One of the principal things that we've tried to talk about this year is that the whole point of much of what we do, as complicated and as crazy as sometimes it feels, we're trying to figure out where the object is at some time in the future. We want to predict the motion of an object. It might be the motion of a system of objects, and it might be a complicated system. But our goal has been to be able to predict the motion of an object. And knowing where it is only part of the story, right? We've talked about three principal things that we generally want to know about when it comes to an object's motion. Its location, how fast it's going, and if that value is changing, right? So it's acceleration, velocity, and position. Now, we've developed other things that talk about those three things, like momentum and energy, quantities that we know have relationships with other factors in the universe. But when we boil it all down, we tend to try and look at where is the object, how fast is it going, and is that changing? Because if we know that, we can probably predict where it's going to be in the future. And that tends to be part of our goal. So one of the things I want to speak about today is the idea of simple harmonic motion. I tried to get us introduced to that yesterday in the limited context and the time that we had. And I could go and talk about it for a long period of time, but I prefer, unfortunately, that we focus a little bit. Only in that there's limited time. And I want to get to some of the stuff. So let me think of the absolute simplest harmonic oscillator I can. And the simplest harmonic oscillator I can think of is just a box connected to a spring. I want to make this on a slick surface. Now, this by itself isn't a harmonic oscillator. It's not a harmonic oscillator until I give it some energy or get it moving. Then we'll see how it behaves, and that's how we determine whether it's a harmonic oscillator or not. One way to do that, of course, is to take our starting point here and maybe take the mass and pull it out, a small amount. This will stretch the spring clearly, because we've now moved the object outwards a distance x. Now, if we wanted to study this, figure out what it's going to do, then we could probably find a law that we could use to study it. Now, what law would that be? What's that? Hooke's law would tell me about the spring, sure. What Hooke's law would do is it would tell me the force from the spring on the box. And it would say that that force is equivalent to how far we pulled the spring out minus the spring constant of the spring. But it's a vector equation, because it also gives us the direction of that force. It says that that force is directed in opposition to the position. So if I move the spring out, I would get a force back towards equilibrium. All right. Well, you brought up force. So if we're going to evaluate how this object moves, and we want to use forces to do so, which of our kind of fundamental units is the one we should look to? And we have energy, momentum, and Newton's laws. It'd be nice to talk about energy, sure. It'd be great to. The problem is that what about this is connected directly to energy that can tell us where the object is at some point in the future? Yeah? It tells us how much energy is in the spring. I'm not sure it tells us where the object is in the future. Maybe. There might be a way to it. But I think we're probably going to have to go more fundamental. I mean, probably. Now, I'm not saying we can't do what you're suggesting. I'm just not going to. I'm going to start someplace more fundamental. What's more fundamental than talking about energy then? Yeah. The reason I want to start there is because of something I prompted you with earlier. If I wanted to create an equation that could be used to predict the future, one of the things that we could use would be our ideas about motion equations, right? We know a little bit about that. And Newton's laws help us build that because they have acceleration built into them, right? It's right there in Newton's laws. Now, look at the forces acting on the box. There are probably more than just one force. There's probably others. But which force matters? I think the spring, right? There's a weight and there's normal force, but those are balanced, unless I put this on some kind of ramp or something. So for the time being, I think the only force that's actually causing motion is the spring. The moment I let go of the box, it's the spring that's going to cause the box to move to the left, correct? Now, we can immediately figure out how much acceleration there is by just solving this for A. The problem I have is if I wanted to figure out, say, how fast the box will be going after a few moments, can this relationship tell me that straight away? Why not? What's wrong with this relationship telling me that? What's that? Have velocity in it, doesn't have time in it. But more importantly, does the acceleration stay the same? In the moment the box has moved a small amount to the left, doesn't the acceleration also change? The moment we have something where we have a non-constant acceleration, we can't use any of the motion equations we know from before, we may have to create our new motion equations. And you and I both know that the best way to find a new motion equation is to start with a differential equation. That's where we started before, because we know something about accelerations and velocities. We know that acceleration is related to velocity. Right? We know acceleration is dv dt. So maybe, if we do this, we could start to create a differential equation. In fact, I did say to you, probably the best place to start in creating a differential equation is to start with Newton's second law because it has a differential in it. And we've done this like this before. Do you remember when we talked about, say, air resistance? Air resistance was proportional to velocity. When we did this substitution, we got a new relationship that had a differential in it, and that differential was reflected on the other side somewhere. Something about the object's air resistance. The problem is that we don't have velocity on the other side. What do we have on the other side? Position. But we know something about velocity and position, don't we? We know velocity is the rate of change of position. We could just smash these things together. Right? Meaning, take the v out and put dx dt in. Wouldn't that work? It's still a differential equation. But this is different, right? This is taking the derivative of a function, then taking that derivative again. So this is two derivatives. In fact, we have a way of writing this, some symbology. It's ridiculous symbology, but you take the two d's and you act like you're squaring them. And then you take the dt's and you square it too. You're not actually squaring it. This is symbology. This symbology means second derivative. This is a second order differential equation because our derivative is the second derivative of a value. Now, just so you guys are completely made smarter today, writing second derivatives occurs a lot in science, and so there is shorthand for derivatives. We don't use it in this class, but it is possible your professors in college will bring it up and expect that you've been taught it. there's at least 4 different ways to write the derivative. At least 4 different ways that I've seen and I've been taught through the years. One of the more common is dot notation. A dot over the top of the variable represents the number of derivatives with respect to time. It's a very, I mean, it's simple and somewhat elegant, but you have to be in the in club to know that that's there. And if nobody tells you that's true, then you don't know about it. But it's specific about single derivatives with respect to time, since they tend to happen a lot, especially in physics. So dot notation is pretty common. So x dot would be the first derivative with respect to time. X double dot would be the second derivative. There's also places where they use bars. It's similar. But if you see your professor doing something like this and you're confused, ask the professor. Ask him what the symbols mean. That way you know. Otherwise, you'll do what I did my first couple of weeks and not know what he was talking about because I was too intimidated to ask him a question. So I'd encourage you. I don't know what the dot means, Mr. So-and-so, and they'll tell you. We're not going to do that because we just touched the surface here. So we'll continue with this really bulky kind of notation. All right? Now, herein lies the biggest problem. We can't just split the derivative as we've been taught in the past. There's not a way to do that. We have to come up with something else, a different way to do this. But I think one of the problems that you guys tend to have is not being able to read what this is actually telling you. As I said from the beginning of the year in talking about calculus, calculus is the algebra of functions. Algebra is about the relationships between numbers, but calculus is about the relationships between functions. So this is expressly telling you about a relationship between a function. In fact, let's solve it for the derivative, which would have been our first step in solving a differential equation anyways. So I'm going to solve it for the derivative and get minus k over m times x. Now, x is a function. X is some function that has to do with t. Right? It's a function. There's going to be some equation on the other side of that has t in it somewhere. What this differential equation says, if you read it the way it's intended, is it says if you have a function that changes with time and you take the derivative 2 times, you'll get back the original function multiplied by a constant. That's all it says. And I know you're looking at me. I can see that look. Here's a function. This is a function, right? It's a function that has t in it. What's the first derivative of this function? I'm doing this on purpose. What's the next derivative? So 6 times, well, just 4, 4t. All right? Now, I've taken the second derivative. I have 2 functions to compare. Here's my original function, 4t cubed. When I look down a ways, I get a constant, but I don't get my original function here. So obviously 4t cubed doesn't work, does it? This wouldn't satisfy this condition. Can you think of a function that when you take the derivative, you get back the original function? Some of you got to know. Yeah? E to the x. Let's start with that. I don't know why it is. Now, if I do, and I don't want to do x because we're talking about t, so I'll take e to the t. So e to the t, and that means dx dt will be, well, e to the t. And the second derivative of the position will be, well, e to the t. Let's class it up a little bit, maybe. Like, could we do something to get a constant out front? Go ahead.
Multiply t by a number.
Okay, how about just a letter? You picked the letter. You offered it. A. All right, e to the at. When I take the derivative of e to the at, what do I get when I take the first derivative? A times e to the at. Excellent. When I take the second derivative, what do I get? A squared e to the at. Excellent. I have my original function, and I have a constant. Looks like this could work, except for one important detail. There's a negative sign there, right? Would it work to put a negative sign here? Well, for the people who don't know why, let's go ahead and tell them why, because some of them don't know why. The first derivative would be fine. I'd get the negative sign there. The problem is the second derivative, I'd get a negative times a negative, and it would cancel out, and I'm back to positive, so that will not work. Now, although this process, guessing at an answer, can be lucrative, it really helps if we get the right answer out of it, and this is not it. So I know somebody in the room will probably be able to point this out, so I'd hate to steal their thunder a little bit. Can somebody name a function that when I take the second derivative, a negative sign will persist? Yeah? Cosine. If I take the first derivative of cosine, I do pop out a negative sign, don't I? I could choose sine or cosine, it'll probably work, right? First derivative of sine gives me cosine, but again, second derivative of the cosine would give me the negative sign I would need, right? So which one do you guys want to start with, sine or cosine? It's gonna make it makes a difference, to be honest, but let's just let you pick. That way you can understand why you might choose one over the other. So which one do you guys want to start with? All right. And we are learned people now, so let's advance this a little bit because I don't want to spend so much time going backwards. I don't think sine is the appropriate function to use on its own, right? Because it's not going to just be sine of t, is it? We're probably going to, because we know we have to have a constant that pops out eventually, so we should probably put something in there. Wouldn't you agree? We'll stick with the a given to us from the start. Also, this is just a small thing, but x is in meters. Sine has no units, right? But this is an object that's going to be moving. So I think if it's sine, we know it's going to go up to a maximum and in the other direction a maximum. So I'm going to put whatever that maximum is, that position, something that has meters in it, right? Sine by itself wouldn't. Follow me so far? This is not accidental. I think you'll get it in a minute. And I think I can do that with this class. Well, let's take the first derivative, shall we? What is derivative of sine? All right, so I have my x out here first because it's just a constant. I'm going to get that a, sure, and then I'm going to have the cosine of at. Excellent. So let's go ahead and do this again, shall we? Except this time, when I take the derivative of cosine, what do I get? I'll get a negative, sure. I'll get another a, won't I? Still going to have this x, but now I'm back to sine. This is my original function. Do you see my original function here? I think this works. Now, I said to you, we should look at both. And I don't think it's too much to ask to do this again. Take the first derivative, what would I get? Take the derivative again, what do I get? All right. So I have two possibilities. One of these is a better choice than the other. But to get to that understanding, we probably should go all the way back to this picture. Why is one of these a better choice? Go ahead.
Because it doesn't start at 0.
I pulled the object out, and when I released it, was it at its starting position? No. It started away from the origin, and it's going to go back towards the origin, so this looks like this is as far out as it's going to go, and cosine starts at 1. So do you see why cosine might be a better choice here than sine? All right. Now, I'm going to stop right here. You know, these things have some meaning here. So first, and I'm going to stick with the cosine as our start. So we'll get rid of all of those. And this represents x as a function of t. This represents the first derivative, which is what? And this represents our second derivative, which is what? There we go. And it looks like, based on what we've done so far, that a has got to be something to do with k over m. Correct? In fact, I think we can all probably agree that a squared is k over m. Right, for our spring mass. So we could rewrite this if we wanted to be more related to our function. This would be the square root of k over m times t. This would be minus the square root of k, Mr. Shelton. Do better. Minus the square root of k over m times x naught sine square root of k over m times t. And this would be minus k over m x naught cosine square root of k over m times t. It's a lot of writing k over m's and stuff. We could probably simplify that, but right now I want to be as explicit as possible. Now, we derived 3 motion equations by recognizing how the derivatives were related to the original function, and then created them by just taking the derivative of our function that we guessed at, right? That's all we did. But we started with a function that began with net force equals ma, right? And this parameter is a function of the spring constant and the mass. Something about the force that was pulling it back to equilibrium. Something that we call the restoring force. All oscillators will have a restoring force, something that will move the object back to equilibrium. But the bottom part is inertia. Now, if we really want to understand what's happening here, let's take a close look at our position function. So I want to kind of take the position function by itself and ask you a couple of quick questions about it that I think you can answer. Cosine repeats itself, right? When does cosine repeat itself? Every 2 pi? So when everything in here reaches 2 pi, we get back to where we started, correct? So that suggests, if we take all of that, but put in the time it takes to repeat, called the period. Right, we said that before. The period is the time it takes something to repeat. When those two things multiply together, we must get something that is equal to 2 pi, or 4 pi, or 8 pi, or something like that. Something that's a multiple of 2 pi, correct? That must mean that the period of oscillation must be this. Right, all I did was solve for t. But I'd solve for it setting it equal to 2 pi. Now, hear me out. This suggests we could test real quick to see if this works. Because What happens when I make the mass bigger? Should it go slower or faster? I'm not trying to trick you. When m gets bigger, t gets bigger, right? Meaning it'll take longer to repeat. Seems like it's going to go slower. If we're looking at the functions, this has to be the max of our function, doesn't it? That means this has to be v max, the fastest the object will travel. I mean, this has to be true because it's a sine function, and so it can't get any greater than that. That must be the fastest it's going to go. In fact, if I apply that logic here, this has to be a max, right? Now, this one we already knew. I want you to think about it. Didn't we already know that one? Had to be true. That's when we just launched it. We pulled it back. That's when the force was the greatest. That's when the acceleration was the greatest. So we had to get net force back out of this, right? Now, the acceleration is changing all the time. In fact, we should be able to see that pretty clearly too. So let's make this that mustard yellow color. It's unfortunate that it looks like in our test subject that, but I want to point something out. Any time we get a function that has acceleration proportional to position with a negative sign in there, anytime, whatever's in here, that controls the oscillation. Both of these are equations for oscillators, whether it's linear acceleration or angular acceleration. These are both equations for oscillators. Because of that, if you can form this equation, whatever's in that parenthesis, it controls our function. It is the a squared of our function. Right where A was for any of them. So we want to look for oscillators. And to do so, to get here, our net force or our net torque has to be proportional to a negative sign, a constant, and a displacement. If this is true, then that's the consequence. If this is true, that's the consequence. And they oscillate. Because we started here. So anytime the second derivative is proportional to the position, and we get a negative sign in there, we have an oscillator. Now, there's a few more little things I want to throw in here. But let's consider, I think we can talk about a pendulum really quickly. But a pendulum is a circular oscillator, right? It's a circular oscillator, meaning it's rotating, isn't it? Pivot point, torque acting on the mass. So let's throw it together. I don't think I have to hurry too much, because I don't think this will take that long. I do have to draw a picture, though. When I displace it an angle theta, there will be a force that will act to return it back to equilibrium. Would you guys agree? That force comes from gravity acting at the mass. Is that all good? I think this constitutes a torque. Wouldn't you? Do you guys see why I'm saying a torque? Because I have a force acting at the end of a torque arm, say of length L. All good so far? Need to be careful because We know that torques are based on this angle here, but can we agree that this angle must be theta? So I'm going to start where we started with the other one. Net torque equals I alpha. Torque. Torque is R cross F. Or better yet, R times F times the sine of our angle. So let's see what this torque is. What's R in this case? What is the distance from the pivot point to where the force is applied? What's that? L. The size of the force is gravity, isn't it? And then we've got the sine of theta. This has to equal I. Well, what's I? What kind of moment of inertia should I use here? Point mass. Point mass is mx squared, but what's x in this case? Times alpha. Now, I would say theta is rotated into the board using the right-hand rule, but my torque is out of the board. Would you agree? So theta is positive, but our torque is clearly negative. Solve this for alpha. Alpha equals negative, let's see what's in the parentheses here, LMG over ML squared sine of theta. All right. Something's wrong, isn't it? This doesn't look like an oscillator. It's so close, isn't it? But this is sine of theta, not theta. So I think we have a problem. We're close. We know it does the thing. All right, so we'll have to figure this out tomorrow. All right.